use less capacitance. Now I'm thinking some ways that we can overcome this, but let me check a little bit about the other outputs of the counter. Maybe we can use one of the other outputs instead of the HFO and then require the opposite capacitance. But let me check it a little bit and see how it turns out. So the things I've tried is to connect the input instead of the HFO to the VFO or to the BFO, and none of them worked. The frequency was a little bit lower than 0, but I could not set it to the right frequency. So at minimum capacitance I could set it even below than 0, and at the maximum capacitance it never reached 0. So these two inputs go the other way around. So we're going to use the HFO anyway, but the maximum we can get is 500 Hertz here. Okay, that's the maximum we can get. So I have to figure out another way of doing it and see how it goes. Back on the manual, in the circuit description section, it says that the frequency display is actually doing an up counting on the high frequency oscillator, and then in the VFO, the linear master oscillator, it does a countdown. It counts down, and in the beat frequency oscillator it also counts down. And this is what we have shown with our experiment before. So a way of doing it would be to put an external oscillator, low frequency oscillator, 500 Hertz oscillator, and connect it to the LMO input or to the BFO input, and then 500 Hertz will be automatically subtracted from our frequency reading. I will try to avoid this. I don't want to actually build another oscillator just for this unit and have it power it on. If we can't do it otherwise, I'm gonna do it that way, but I'm trying to find out how else it can be done. And so I'm fiddling around again with the crystal frequency at this point, and I'll try first to put a smaller value of capacitor there. Let's say I'm gonna either remove this capacitor and put and see if I have any 1 picofarad capacitors there. They're more difficult to find out, but I might have some, and see how it goes. If this 1 picofarad of difference does any good or not. And the other thing I could do is I could just I put a series capacitor with this variable capacitor. So instead of 2 to 16 picofarads, for example, I may put a 2 picofarads or even a 1 picofarad capacitor, and then I'm gonna have a very small capacitor there, yet adjustable, but with very low adjusting range. But we don't need a very high adjusting range. Even 2 picofarads is too much at this point, so we don't need much more capacitance than 2 picofarads. Okay, and we might end up completely removing this variable capacitor. I don't know, maybe the traces are close enough on this variable capacitor, the PCB traces, and maybe that's enough. But really it would be nice if we had a way to vary very small capacitances here. So I think I'm gonna try the series capacitor method, and see how it goes. And it turns out that I had quite a few of these 0.3 to 2 picofarad capacitors, piston trimmers, and I hadn't found an application for them until now. And to be able to actually measure such low capacitance, you need some very special instruments, and currently I'm going to use a very old instrument, the Tektronix 130, which is capable of measuring such low capacitances, and I'm going to measure one of these trimmers. But first I'm going to zero the meter, just like so. And then the probes are all ready to close, which should be, and then just clip one of them, clip both of them to the capacitor, the piston trimmer, and then I read that minimum capacitance are in 0.3 picofarads. And as I go up and adjust the trimmer, now that's a little bit difficult to do with one hand, but as I go through, let me reposition the camera as I'm doing this, and that's actually multi-turn trimmer, so I can very finely adjust. You see the capacitance starts to rise. I'm doing this with one hand now, and it's very difficult. The capacitor is hanging on those probes. As I insert the screw more on this capacitor, I have a larger capacitance, and it goes 1.5, 1.8, close to 1.9, yeah, 1.9 picofarads. Let's check out the zero of the meter again. Yeah, it's a little bit off, so we have to zero it again, just like so. I have not allowed the instrument to heat up very well. This is just the capacitance of my hand now. I'm trying to do everything with one hand here. It's a little bit, yeah, here we go. Yeah, so now the capacitor is fully in full capacitance, and it's just at 2 picofarads. So yeah, with this nice LC meter, we are able to do such things and much more. That's the nice bit of this meter. Not so much the capacitance range, but this one. But anyway, this is for another video. So I'm going to use one of these trimmer capacitors and replace this 2 to 16 picofarads capacitor here, and let's see how it goes. Hopefully the lower capacitance won't stop the oscillator from working, and we can get closer to the 0 bit here, closer to the frequency we need. So I'm going to replace this and come back. Back in the bench. The problem is that to replace this capacitor here, you have to actually disassemble the whole PCB here, all those screws, and you have to remove the cover of the tubes here, of the nixes, and remove these screws which hold the plastic one, and then even then you have those cables here that don't allow you to completely remove the PCB but just bend it over. So it was easier to just connect this little trimmer in series with the main trimmer. So here you see the main trimmer, and I have just cut with a fine cutter, this leg here, and not completely. One of them is going to the PCB, that point that I have soldered, and it's bent a little bit on the right, and the other stays on the air here. And between this pin of the main capacitor and the other pin that goes to the PCB, I have soldered this fine trimmer, and this should in theory yield to even less capacitance at 0.3 picofarads. And it turned out to be quite solid actually. The trimmer cannot move at all, so it will be very fine, and I can adjust it from the top here, so it will be very fine. It will be very nice adjustment, I think, and solid. And that's the advantage of doing so also, is that I keep the original trimmer there, and in case in the future I want to do something, I want to revert this modification, I can just remove this trimmer, or if I want to be quick here, I can just short these two connections, okay? So yeah, I think it turned out really well, at least mechanically. So let's see how it behaves on the actual circuit. Back in the shack, it turns out that I can never set the frequency below 2 to 400 of hertz. So I think we're as close as we can. We didn't have much overhead here. By lowering down the capacitance that much, we get to a point that the oscillator stops working here, inside here. So another 1 megahertz crystal might help, but I don't have any of these around, so I don't know what else I can do. Okay, I think we're getting results now. Now I'm at 7.2 megahertz, and let's check it out. 7.2. Okay, and we could do it even better. Let's see. Let's see if we're tuned. 1, 2, 3. We're not too tuned. Let me leave this phone there for a moment and tune. 1, hola. Okay, now the rig is tuned correctly. As you can hear, it's tuned correctly to 7.2, that rig. And now we're going to check the frequency. 7.2 exactly. You see? So I think we're doing fine here. And what I actually did was the trimmer was not behaving correctly here, so I've changed the let's focus a little bit better. I've changed this trimmer to a fixed capacitor of 8.2 picofarads. So actually now we have this main trimmer, the original trimmer, connected to a fixed capacitor in series with a fixed capacitor of 8.2 picofarads. And